particular compound? H2O. I'm liking it. Awesome, awesome. So let's pick on H2O before we kind of dive into the next topic. So H2O looks like this, right? Now, not today, but on Monday probably, we'll be talking about how do we draw kind of the structure. You already kind of know it has an oxygen and 2 hydrogens. And I think I told you the other day, this is your covalent bond. That dash, one line, we call it a dash, is your covalent bond. Actually, 2 electrons. Anytime you see a dash on a picture like this, that means 2 electrons are there. They're being shared between those 2 atoms. So let's go ahead and can you tell me for hydrogen, how many valence electrons are there for hydrogen? 1. That's right. There's only 1 electron around hydrogen, and it's a valence electron. So this is how I do this. For hydrogen, the element hydrogen, there are 2 hydrogen atoms. They each have 1 valence electron. Okay. For oxygen, there's 1 oxygen atom, and how many valence electrons does it have? 8. Nope, not 8. It's the group number. 6. Perfect. Yep. 6 electrons. Yep. So there are 8 electrons that can be shared with these 3 atoms. So here's kind of how this looks like. We have the oxygen, and we said it has 6, so I'll go ahead and make its X's. These are electrons. These are the valence electrons. See how I do that? Yeah. Looks kind of like I'm doing a football diagram there. Okay, so do I have 6? Yep. And then what happens is I'm going to go ahead and shimmy up a hydrogen, and I'm going to make its valence electron a dot. And its valence electron over here a dot. So my point is going to be when we talk about these covalent bonds, it's these electrons that are shared between, in this case, the oxygen and the hydrogen. These are shared. That's it. Shared to make a covalent bond. Now, there is a little bit of, and we're going to talk about something called electronegativity. And the video we watched talked about it a little bit. Let's see how I do this. So, I know, like if you've ever been sharing a box of chocolates, oh my gosh, I haven't made it to the after Valentine's Day sales. I should not go. It's probably right. But sharing a box of chocolates, and if you're like me and my husband, I love it, and he just kind of likes it. So with regard to that box of chocolates, I'm probably going to eat most of them, and he'll eat a few of them. If that was electrons or whatever, I would have a greater electronegativity because I'm hoarding the chocolates. And that's actually what atoms do too. Atoms hoard electrons to themselves. Now there's only a pair of electrons to be hoarded, but they get more of the, like if you have joint custody, they get more of the electrons more of the time than the other atom. That's a high electronegativity. Okay, that's it. So what do you think? So electrons are negatively charged, right? I'll just go ahead and tell you that the electronegativity, and we use this symbol, looks like an X. This is our symbol for electronegativity. It's the Greek letter chi. The electronegativity for oxygen is high. Chi is high. Electronegativity is high. So does this make sense that when it comes to looking at an oxygen atom, it's running around with a kind of a negative charge? It's not an anion, but it eats more chocolate. It has more electrons. It's actually what we call partially negative, so we kind of do this funky S to kind of show it's partially negative. So that's to say these 2 electrons are going to buzz around the oxygen more than the hydrogen. If it's partially negative, what's the hydrogen then? What's the opposite of negative? Positive. Yep. Partially positive, partially positive. Yep. So that all has to do with electronegativity. Electronegativity, think chocolate. So if you have an affinity for chocolate, you have an affinity to eat chocolate. So if you have an affinity for electrons, you have an affinity to hold electrons to yourself, and that's all it is. So the greater electronegativity an atom has, the more it attracts electrons to itself. I went ahead and printed this because I want to look at this here in a minute. So where's the jag on this picture? The blue and the pink. Yep, the jag is right between the blue and the pink. Perfect. So what's over here? Metals or non-metals? These are metals. Yep, and these are non-metals. Now look at the top of the sheet you're going to use for your test. What did we put at the top of the column for 1A? Plus 1, exactly. Now, if something wants to be a plus 1, is it going to be kicking off electrons or bringing in electrons? It wants to be a plus 1. It wants to be have a positive charge. So electrons are negative, so when you're going to bring electrons in, you're going to kick them off. Kick them off, yeah. So kind of along those lines then, our metals have low electronegativities. Makes sense. I'm going to kick them off. They don't want to kick them off. I can't believe it. Every once in a while you run into people who don't want to. Okay. Very good. We've run into deltas before. A delta is a triangle. Delta is a Greek letter, right? Deltas mean change in. Remember that? Delta, change in. So change in electronegativity. All that is what you do is if you have atom A and atom B joined together, what you do is you calculate the electronegativity of A minus the electronegativity of B. What are these lines here?
It makes whatever's inside of it positive.
It does. It makes whatever's inside of it positive. It's the absolute value of perfect. You got it. So somebody help me out. What is the electronegativity difference right there for that bond? So delta chi there. So what is the electronegativity value for hydrogen? In the previous slide. Because you might need to use this for your homework, I'm not sure. So what's that value for hydrogen? 2.1, yep. What is it for oxygen?
3.5.
3.5. And don't feel bad if you get your calculator out, because I do that sometimes. But I'll go ahead and take 3.5 minus 2.1. I get what, 1.4? Well, an absolute value makes it positive. So it's 1.4. That's the electronegativity difference between that oxygen and the hydrogen atom that are stuck together. So here we have electronegativity difference, and I hid these from you guys, didn't I? So you have to fill them in. Did I? Okay. No, they're there? Oh, you have the number, okay. So if something's nonpolar, oh, I didn't finish that thought. So nonpolar. If somebody's personality has got a polarizing, it's usually kind of a negative thing. Somebody has a polarizing personality. That means they walk into the room, and some people are attracted to them, and some people are repulsed by them. That's a polarizing personality. So just as I've done for this water molecule, what we have up here is we have a polar situation. This is a polar, anytime you have a partially positive, partially negative situation. But can you see where if you were to go ahead and calculate the electronegativity difference is 0, that means that actually when it comes to sharing chocolate, they share equally. A good example is oxygen. Oxygen is one of those elements, I think we talked about this, that always wants to have a buddy. So we have an oxygen bonded to an oxygen. Okay, and if I were to come up with if I were to analyze that bond, I would say the electronegativity difference is, what's electronegativity for oxygen? Absolutely, 3.5. I was over there too, wasn't it? 3.5 minus 3.5. I can do that without a calculator. Electronegativity difference is 0. Okay, there is no partially positive, partially negative. It's just flat. It's what we say nonpolar, which is nice. Now, if you go ahead and connect a couple of atoms and you do this little subtraction and you come up with electronegativity difference, a delta chi of 0.5, then it's weakly polar. And it kind of goes up from there. 1.0 polar, 1.2 strongly polar. Ooh, what were we up here for? Goodness. For this water molecule, we were 1.4. We were even greater than 1.2, strongly polar. Well, we could go back to my husband sharing a box of chocolates with my husband, which I have to go out and buy chocolates. I just have to do that now. So if I keep going crazy about I just have an affinity for chocolate, I'm sorry, hon, that's it. He basically gets none, and I get all of them. Okay, and then in the world of chemistry, what happens then is an electron can be entirely transferred. Oh, I know, here's an analogy. In that case, not only do I eat my entire box, but he gave me a box. So that would be an electron that's transferred, okay, to the one that's more electronegative. And by the way, I hope we're all on the same page. When you guys told me a minute ago that at the top of 1A you put a +1, what'd you put at the top of 7A, group 7A? A -1. Mm-hmm. So that's an example of a +1 that kicked off an electron. A -1, it took in an electron. Exactly. So my point was going to be that if you have a cation, a plus, and an anion, a negative, what forms between those two is now an ionic bond. Makes an ionic compound. So what's an example of an ionic compound, we said? NaCl. Very good. Yes. Yep. Perfect. So we have these kind of building up to a high electronegativity difference where an electron's transferred. These are all where electrons are shared. So covalent bonds, electrons are shared. Not necessarily shared equally. So here I have something, this could be like an O2. It's a pretty molecule, isn't it? Where the atoms actually might be the same. So when you come up with electronegativity difference, there is none. Now, what you're going to see is if you see something kind of bigger around something in these figures, that means it has more electrons. Okay, if I were to draw this kind of, I don't want to say kind of 3D, this would be, the oxygen would be swelled because it has more custody of electrons. It's partially negative. Electron transfer. Now I said 1.7 is kind of the threshold for the electronegativity difference, the delta chi, but sometimes different chemists will say different things. Here we have, this is a polar molecule. You see that, and actually that's a lowercase delta, that kind of funky looking S thing, that's actually lowercase delta. So partially, but it means partially. So we have partially negative, more electrons, partially positive, less electrons. Just have another figure to kind of show you that. Cl2 molecules, kind of like an O2 molecule, where they're shared equally. Pure covalent. We said sodium chloride. You told me is an example of where the electronegativity of the chlorine atom is high enough to abscond on with an electron. Okay, all of it's +1 of sodiums. And so the chlorine is a -1, the sodium is a +1. Then you have an ionic bond between the two. HCl, if we were to look up the electronegativities of the hydrogen and the chlorine, you'd see that bond is less than, or that electronegativity difference is less than that 1.7 threshold. But the chlorine is kind of swollen there. It actually has more electron custody than the hydrogen, so it's partially negative. So these will we do when we meet again on Monday. Remember, next week's a short week. We don't have class on Friday. Let's see what else we get through. Oh yeah. Binary, what does binary mean? Bicycle, binary. Two. Binary means two, yep. So we're going to talk about binary compounds like sodium chloride. Why is it binary? Because we have sodium and we have chlorine. Okay. So the things you're going to need to be able to do with regard to this topic is to be able to write the formula like NaCl and then give it a name, sodium chloride. So we'll talk about that. And so in this case, we're going to be actually mixing, and it's kind of like granimals where you used to like clothes where little kids used to be able to go to the closet and match them. Like I'm bad at matching things sometimes. But what we're going to do is go to our closet. We're going to go to our cation closet. Notice I'm kind of going over here, our cation closet. We're going to go to our anion closet and just pick one of these and pick one of these and put them together. It's kind of fun making ionic compounds. But when we write our formula, like NaCl for sodium chloride, the formula needs to actually have an overall neutral charge, and I'll talk about what that looks like. Now, you guys told me the other day when I asked you the formula of sodium chloride, you told me NaCl. You didn't say Na plus Cl minus, did you? No, because you just don't do the charges in the formula. So sodium, cation, chlorine, anion. Actually, you can use sodium chloride as a good, if you're in this subject and trying to figure out now, how does that work? Well, just remember table salt. Take it apart and apply it to some other things. It's always the cation first and then the anion, which actually on the periodic table, it's the cation metal and the anion non-metal. So it works. So for sodium chloride, what you do, you call it sodium because the cation was sodium. Now you didn't call it sodium chlorine, did you? That's one of the things we're going to hit today a little bit. You called it sodium chloride. So one of the things is for that non-metal anion, you have to lop off the end and throw on an ID as in dog, IDE. So let's talk about neutral formulas. What does that mean? Well, I know this says a different compound, but let's just go back to your NaCl. That's the formula. We all know that. That works. Now to pick it apart, you guys would tell me that the Na is a +1 and the Cl is a -1. That's at the top of the columns. So to make sure it's neutral, it's like this little math, a little bit of math. So we have one sodium atom, it's a +1, and we have one chlorine atom, and it's a -1. And if you add that up, I know you're like, oh, that's silly, but if you add that up, what do you get? You get 0. This is a -1. 1 times +1 plus 1 times -1 is 0. That's what I mean by neutral. That's neutral. That's totally neutral. So let's apply that for sodium sulfide up here. So Na, they've already told us the formula is Na2S. So help me out. Na is a +1. Well, what's S? What did you put up there for S? The top of the column. -2. Okay, so let's see. Let's go ahead and see what we got here. We have we have 2 sodium atoms, and they are both a +1. Oops, sorry. And we have 1 sulfur atom, and it is a -2. What's that add up to? What's that? 0 again. And that's what we mean by neutral. Your pluses and your minuses need to be a wash. So we could kind of look at it this way, where these are valence electrons. So sodium has 1 valence electron, sulfur has 6. and you can see it kind of, the sodium will give up an electron between the two of them, and they'll give the sulfur a complete set of 8 electrons. So, did we talk about this? When sulfur picks up 2 electrons, what element is it like? It has the heart of the sodium atom, but electrons like A. Because its sulfur has 16 electrons, so what has 18 electrons? Argon, yep. Has the heart of the sulfur atom, but the electrons of an argon atom when it picks up those 2 electrons. So it's a -2 charge, just like you have at the top of the column, and the sodiums are +1 charges. Now, let's pick on sodium. Sodium, when it kicks off an electron, where is sodium? When it kicks off an electron, it used to have 11 electrons, now it has 10 electrons. So if it has the heart of the sodium atom, but the electrons of something that has 10 electrons, what element is that? You don't know? What element when it's neutral has 10 electrons? Neon, yep. So when sodium kicked off an electron, now it has 10 electrons, and it has the heart again, like a sodium atom, but the electrons of neon atom. So we kind of have this losing electrons and gaining electrons. You see the pattern to get like these guys over here. Magnesium chloride. So let's kind of do our check here. They're already telling us the formula is MgCl2. So help me out. Magnesium, what sort of ion does it form? What's at the top of the column?
+2.
+2, very good. How about chlorine? It's -1, didn't we? Okay, so let's do the math. I've got 1 magnesium, and it's a +2, and I've got 2 chlorines, and they're both a -1. So I'm liking 0. So that's how that works. That's a neutral formula. So let's kind of look at what that looks like. Oh, I guess that's all it is. Okay. So we're going to go around the room, and we'll start with you, Miss Jasmine. See, I deleted these this time. I was much smarter. So what element is O? I'll ask you. Oxygen. Very good. If you take the word oxygen, take off the -gen and replace with IDE, what do you get? Close. Oxide. Oxide. Yep. I think I told you wrong. It's something like that. You keep the OX, that's it. That's all you keep. Oxide. Okay, so Nadira, what's nitrogen stand for? What's N stand for?
Nitrogen.
N stands for nitrogen. So if you just keep the first few letters and lop it off and put IDE on it instead.
Nitride.
It is nitride. Very good. What is S stand for?
Sulfur.
It's a sulfur. So
Sulfide.
sulfide. Perfect. You got it. Hannah, Cl stands for?
Chlorine.
Yep. So what would chloride? Very good. Very good. So Kate, H stands for?
Hydrogen.
Hydrogen. Don't keep much of the name, but first part of the name.
Hydride.
Hydride. Hydride. We're back to you, Jasmine. What's Br stand for? Bromine. Yep. Bromine. So keep the first part and bromide. Perfect. And the dear, what's P stand for?
Phosphorus.
Yep. So
Phosphide.
phosphide. Phosphide. Phosphide. Yep. Very good. It's What's F stand for, Mackenzie?
Fluorine.
Fluorine.
So fluoride.
Fluoride, yep. There's a big toothpaste, you know, and they don't talk about fluorine, they talk about fluoride being in it. So that's the ion. So fluorine's a neutral molecule, or atom, excuse me. Fluorine's a atom, and fluoride is the ion. Okay.
Iodine.
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 Iodide. Yeah, iodine or iodine and iodide. Yeah. So this one's like this one gets the for the closest. All you gotta do is change that D to it, or N to a D. It wins. All right. So we're picking up with you, Kate. Let me grab my pen here. And we're going to do this kind of stepwise. Have your periodic table handy. Okay. So, well, how about this way? So, Kate, what's the symbol for potassium and what sort of ion does it form?
K.
K?
+1.
A +1. Perfect. All right, Jasmine, what's the symbol for chlorine and what sort of ion does it form? I'm liking it. Perfect. Now, I call it crisscrossing. And so I'm going to ask you, Nadira, well, I'll ask you, what do you think the neutral formula would be?
1 times a +1 plus 1 times a -1, so it would be 0.
Right. Yep. I like that. So she said 1 times a +1. Sorry. Plus 1 times a -1 equals 0. Perfect. So I'll just still keep with that thought, Nadira. So then how many of each of these do you need? That it's the ones, right?
Yeah.
Okay. So K1, Cl1. Now, I am fine if you want to put little 1 subscripts there, so you can put them there or not. It really, I'm fine either way. I think I'm going to run out of room. So, the next question, Mackenzie, would be, what is the name of this compound?
Potassium chloride.
It is potassium chloride. Perfect. That's it. So we kind of did those kind of in steps. Now, the crisscross I mentioned, let's do it with, I'm going to go back to this one, this magnesium chloride, if that's okay with you. I don't want to throw you off. Well, I'll just go on. Let's go on. So we're on with Hannah. Thanks. So Hannah, what is the symbol and the charge for aluminum?
Al+1.
Awesome. Al +3. Okay, Kate, what about sulfur?
S-2.
S-2. Perfect. Now this is where I'm going to show you my, it's not really fancy, but my fancy crisscross. And then I'll ask for a verification from Jasmine. So what crisscross does is you take the charge of the cation and you make it how many anions you need, and you take the charge of the anion and make it how many cations you need. That's the crisscross. So in this case, it would say that I need 2 sulfurs, and aluminums, I need 2 aluminums and I need 3 sulfurs. Crisscross. I know it looks kind of messy. So the charge on the sulfur was 2, so that's how many aluminums I need. So I'm going to put an Al2, and then I'm going to ask you, Jasmine, to help confirm that's right. And then the charge on the cation was +3, so for the anion I need 3 sulfides. So Jasmine, could you do the number thing and make sure this is neutral? So I'll get you started. We 2 aluminums, and what's the charge on aluminum? Plus 3, perfect. And right here in this formula, I have 3 sulfurs, and how many, what's the charge on the sulfur? If you can read this. It's a -2. So, what do you think? Does that add up to 0? Yeah. So let's call it crisscross. Okay, so then Nadira, what is the name of this compound?
Aluminum sulfide.
It is aluminum sulfide. Cool. Okay, Mackenzie, the symbol for lithium and its charge.
Li +1.
Perfect. And then Hannah, the symbol and charge of bromine.
Br-.
Perfect. And then let's try it this way. If you crisscross or otherwise, what would the formula for the neutral formula be, Kate? Li1 or just simply LiBr. And then I feel like we keep picking on the same people for the same things, but Hannah, so can you verify that's neutral?
Just 1 times the +1 or -1 and +1 times the
Mm-hmm. You got it. Nadira, what's the name?
lithium bromide.
It is. Goodness. Okay. So, Mackenzie, it's a symbol for calcium and its charge.
Ca +2.
Perfect. Hannah, the symbol for oxygen and its charge.
-2.
Oh, -2. Yeah, you guys keep getting the same things. Kate, what would the neutral formula be?
Ca2O2.
Ca2O2. Very good. Crisscrossing. And now, one of the things about this is that we could actually also go with a reduced form. It would just simply be CaO. So either one would be fine. And if we go with CaO, that works because if we only have one of each, that is neutral. Cool. So, Jasmine, we're changing up a little bit. What's the name of this one then?
Calcium oxide.
Very good. You got it. Calcium oxide. Calcium oxide. Perfect. All right. Cesium. Goodness. All right. We'll find cesium on the periodic table. What's its symbol and then what's the charge? Nadira.
Is this supposed to have an A in it?
Maybe.
For 55?
Oh, I don't remember it having an A in it. We'll have to Google that. That's weird.
But yeah, it's that one.
It is.
It's CS with a +1.
Very good.
And iodine is I with a -1.
Perfect. So Mackenzie, neutral formula?
CSI.
I'm liking that, just like the show. And I won't make us do the math. So how would we name that one then, Hannah?
Cesium iodide.
Cesium iodide. I'm going to have to check that out. Cool. You know who you are, Kate. So the symbol and the charge for, let's go with both of those.
+2 and -3.
And -3. All right. I think this one is an easier one to crisscross. So Jasmine, what would the neutral formula be?
Ca3.
Right?
Thank you.
I'm liking it. Perfect. You got it. And then Madeira, name that compound.
Barium nitride.
Yep. Perfect. Any questions about all that? Compounds are ionic compounds all over the place. So that's where I wanted to get to. So these will also be due on Monday. Have a good weekend, everybody. See my movies today.
We can choose a little bit.